This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software. Ever thought about a master's degree to advance your career as a software developer? The UC Irvine 16-month professionally oriented Master of Software Engineering program is made for you. Taught by experts in the field, the program combines hands-on experiences in fundamentals and latest trends with professional development for successful careers after graduation. Hurry, applications for fall 2019 are due December 15th. Visit mse.ics.uci.edu to learn more and start your application today.
This is Nate Black for Software Engineering Radio. My guest today is Jafar Soltani. Jafar is a lead developer at Rare, a UK-based game studio that is part of Microsoft Studios. Jafar leads the deployment pipeline team, which is responsible for continuous delivery of AAA game titles. Jafar, welcome to Software Engineering Radio.
Hello, thank you for having me.
It's great to have you here, Jafar. I'm just going to mention for our listeners that our overall topic today is continuous delivery in games, but continuous delivery is something that we've covered in the past on several shows. And a few resources that our listeners might check out are episode 221, Jez Humble on continuous delivery, and recently episode 340, Brent Laster on Jenkins 2. But our topic today is going to be specifically continuous delivery in games, which provides a unique set of challenges. And your talk is your talk at Pipeline Conference 2018, implementing continuous delivery for AAA games, was something that motivated our discussion today. And that's also something that listeners can check out on YouTube. So, Jafar, briefly before we get started, could you please describe your role at Rare?
Sure. So I've been working at Rare for over 10 years now. And as you mentioned, I lead a deployment pipeline team here at Rare. And this is a team that didn't exist previously on previous games. For the current game that we're developing, which is called Sea of Thieves, which we started about 4 years ago, we knew that we need to adopt continuous delivery, which I'm sure we're going to go through them in this episode. And in order to achieve that, we sat down and discussed, and we said we really need a team focused on helping us to adopt continuous delivery. And that's how this team was formed, and I started leading this team. Because previously we had the tools team, we had the build team, we had a release team, and this is really a team that combines all of these skills in one bigger team. We are about 9-10 developers in our team for the scale of the game that we are working on. And I can go through the different responsibilities that we have if you're interested.
Okay, I think that's something we can talk about a little bit later in the implementation section. Let's first get to some basic definitions so we can have a common understanding about what we're talking about.
Absolutely.
So first, what is continuous delivery?
So continuous delivery is a set of practices that then allows us to release the game to players anytime we want, anytime there is a good reason to do so. And maybe it's worth mentioning at this point, like how the games are developed traditionally, because the games are not generally developed with continuous delivery in mind. Like for us here, even at Rare, this is the first time we are adopting continuous delivery. It's been a long journey. Previously, and this is the same with a lot of other AAA games, that the project takes about usually 3 years and is mostly based on waterfall methodologies, where you have a big planning upfront. You do some, we call it pre-production, which you try to identify the game, the story behind the game. And then once these are all proven, and also some technical challenges, you try to prove them all up front. Then once you got your funding, Then you go into the production, or basically your development, where you develop the game. And towards the end of it, usually the last 3 months or so, is bug fixing phase, where we try to work together, work really long hours, crunch to make sure all the bugs are fixed so we can release at a certain date. And once the game is released, we might do a couple of updates afterwards, and that team then is finished and they go and move on to the next game. So that's the traditional model for this game, because we wanted to develop this game as a service, which means we wanted to release frequently and keep updating the game and adopting the game based on the feedback we receive from our players and our community. That was one of the main reasons that we decided then to apply continuous delivery practices and adopt.
Okay, so normally what you do is a big waterfall process where first you did some validation up front, and I'm curious to find out more about what that validation is that you do before you get the funding. But
Sure.
before we go to that, I want to get a little bit more into continuous delivery and like what it actually is, or how it's how is it different or similar to continuous integration or continuous deployment. You talked about it as being able to release anytime you want
Yes.
to the user. Could you talk about that a little bit more?
Sure.
So how is it related to continuous integration, for example?
Sure. So continuous integration is another set of practices that is a prerequisite for continuous delivery. And when you practice continuous integration, it means everybody is working on the same branch, which is usually called trunk. So all the developers, everybody work in the same branch, and they try to commit to that trunk at least daily. Sometimes it's encouraged to do even more frequently. So you are generally trying to work in small batches, or you don't end up working on a code for like a week and then checking at the end. You try to break it down into smaller incremental steps and then try to check in those changes as regularly as possible. And we then what we do is that we then run a valid set of validation that needs to be really fast on these changes to get fast feedback. So what you also get as part of practicing continuous integration is fast feedback, that your change hasn't broken anything, which ultimately leads to better quality, because the sooner you find out problems, the sooner you can fix them, therefore the overall quality increases. So once you have that in place, then that allows you to, once you validate your game, then it allows you to automate your deployment, which then in turn allows you to then release that if you want. The difference between continuous delivery and continuous deployment is, with continuous deployment, any changes is potentially is pushed to players or to users. So you check in a change, a set of tests, automated tests run, and the end is released to your users. That works great for a lot of web products when updating new version is pretty much seamless for your clients or customers. Whereas with games, similar to mobile applications, because every time you release, we have to go through a certification process that a platform holder like Microsoft, in our case, have. And as part of going through that process, it takes some time, but players then have to download a new version. So imagine every time you try to play the game, is prompt you that, oh, you need to update. That could be quite frustrating if it was happening multiple times a day. So that's one of the challenges here too, because we want to release as frequently as possible, but at the same time, we need to make sure that the experience for our players is still is acceptable.
So continuous integration is a set of practices that results in small incremental changes being checked into the same branch so that you have something that is always releasable with every check-in. And then continuous delivery will result in some artifact that you can potentially push to customers, but not necessarily. And
Yes,
continuous deployment would be if you were pushing those artifacts to customers all the time. So it sounds like you're going to continuous delivery, so you have that releasable artifact, but you're not necessarily deploying it all the time because you're
exactly. That's exactly correct. Yes.
okay. Because you're doing extra validation, but then also you don't want to harass users with every single change list resulting in an update.
Exactly. And another big difference between games and other, like especially like web products, is when you're talking about the game package, the artifact that is generated at the end of the pipeline, it could be 50 gigabyte or even 100 gigabyte. So the size is quite large compared to other software. So you don't want kind of your players to have to keep downloading multiple gigabyte every day. Otherwise, you are fairly soon going to lose a lot of them.
Understood. Yeah. So there's a lot of bandwidth that would potentially be needed there.
Yeah, of course, yeah, and that's one of the things that we constantly work on to make sure what we are releasing, what we are giving to our players, is absolutely the minimum that they need. This change, which the platform such as Xbox provides a great tooling for us because it does some differential checking and only gives to the amounts of bits that has actually changed since the last time they've downloaded, so they don't have to re-download the parts that they already have and hasn't changed.
That's interesting. I'd like to get into more details about the
Sure,
tooling
sure.
after. First, before I move on to the next section, I just wanted to capture something you said earlier because I wanted to ask about what the values are or what the overall goal is that you have for continuous delivery. And what I got out of your description so far is that you get faster feedback because you're able to deploy faster and that this results in higher quality.
That's correct.
Is that it, or is there something I missed?
No, that's quite right. But there are other benefits as well. That's one of the benefits. I can go through the rest as well. So the other benefits are like traditionally we are releasing a huge amount of content to players at the end of that 2 years, 3 years time that I mentioned. Whereas what we try to do in this case, because this is a game as a service, we need to be able to sustainably delivering new features over a long period of time. And that again, we can do this by adopting continuous delivery and making sure we have candidates almost daily and even multiple times a day. The other thing it also helps us is because, as I mentioned, traditionally every time we were releasing the game, everybody were crunching and working long hours, the weekends, and in this model where you are basically sustainably delivering new features and releasing all the time, if you are not adopting continuous delivery, you end up pretty much crunching all the time, and you have instead of continuous delivery, you have continuous crunch, which is not really sustainable and for developers, for ourselves. So we wanted to definitely minimize amount of crunch and overtime that our developers have to do, and therefore have happier developers as a result of that. And I think another main benefit is because traditionally for games, there aren't many automated tests being written. We are heavily relying on an army of manual testers to test the game. But then the problem with that is if we are releasing all the time, that means we need to hire them for all the time. Whereas traditionally, you hire them for the last 6 months of the project. Whereas in this model, you have to basically hire them all the time. And what's even worse is the moment that you don't have them, you don't have any confidence to make any more changes. So it's not really all of that money. It's not really an investment, unlike the automation. Because like once you spend the time and wrote those automations, then they are always going to be there, and you can always run them. Whereas in this case, you pay for having a large manual testing, and as soon as you don't pay for that, then you don't basically have nothing.
If traditionally you have this army of manual testers and now you're starting to rely more on automated tests, does this mean that you have a small number of testers that is always part of the team, or how does the team composition change?
Yes, that's a great question. Yes, that's definitely true. That's definitely true. Like I said previously, we had probably about 100, over 100 testers, I would say, probably on the previous projects. Whereas now we had probably less than even 10 testers, I would say. And quite a few of them were embedded in each, because we have like multiple smaller teams that work on different features of the game. And they were kind of embedded there, providing early feedback for developers. And they are there mainly not to do what the automated tests do for us, but they are there to do what humans are capable of doing. They are there to give us feedback about the game itself, whether it's fun or do some exploratory testing. Obviously, if they find problems that the game crashes or is unstable, they will log bugs and then we go and fix them. But that's not really their job. Their job is there to do the things that are human made of for.
Okay, so they're able to provide more value because instead of just doing things that the automated test could do, they're doing things that only humans can do, which is
Exactly.
maybe some more qualitative or subjective, and computers don't really have ability to do those things.
Definitely, yes, that's correct.
Okay, moving on to the next part of the discussion. We started talking about this a little bit already, but I want to give our listeners a better idea about AAA games, like what they are. And in particular, I think most everyone knows what video games are, but what is it that defines a AAA game?
So AAA games are have certain characteristics. They are mainly written in C++, and they are generally monolithic applications, and is a big team, usually between 300 to 500 people involved in making these games. So they are quite large scale, and they take a long time. As I said, mainly like, it could be from 2 years up to like 3 4 years to work on the game to release. So it takes a long time as well. And there are not many automated tests written. They mainly rely on manual testers. And the other big difference is that they are treated as mainly like box products. So you have this one big release with a lot of celebration, and then a couple of releases afterwards. But other characteristics for maybe for people who play the game is these they usually have an extremely high quality graphics, and these games really push the capabilities of hardware that they run on to the limits. And one of the challenges is always to try to achieve more from the hardware that you have, and the amount of content there is enormous. So you have a big content team, which is part of that 300 to 500 people who are dedicated to develop the environment, the textures, the models, the animations, and all of, and audio as well. So you have different disciplines involved in making the game. So it's not just software developers. You have artists, you have designers, you have some producers as well, and that's pretty much it. And quite a lot of them run on consoles, but at the same time, a lot of them run on PCs.
Do people usually work on a single game over an extended period of time, or do developers hop from one project to another project?
I think it depends on the company, but for us, we mainly work on one game. I think I would say some of the other maybe other companies who work on maybe on smaller games, they can work on multiple games at the same time. But working on these big AAA titles requires so much effort that realistically, with when you need like 300 to 500 people involved for one project, managing like multiple projects at the same time would be quite challenging. So I think it's pretty much like developers working on the same project for a number of years.
I see. What about in terms of specialization? I thought that developers might hop from one project to another if, say, they were really good at a particular aspect of graphics optimization or something like that, or perhaps network programming.
Yes, I mean, we have people who are very specialized. I mean, what we tend to do generally is to promote people to work on different things as opposed to just work on graphics, as you mentioned. Because in terms of the organization and the performance of an organization, when you have generalists and the people who are capable of working on different areas, when there's a need, it's easier to mobilize people and move them to work on those other areas that you need, as opposed to saying us all our, let's say, graphics program are busy, so we can't afford to move them. But there are certain people who really enjoy working, going really, really deep and being extremely specialized in certain areas. But generally, as I said, we promote developers here to work on as many areas as they can. And for instance, when I started my career at Rare, I was doing graphics programming on Viva Pinata 2 and Banjo Kazooie, and then I moved into tools development and eventually the deployment pipeline team. So it's quite often that people, especially in our company, move around a lot.
I see. That's interesting.
Yes, and it helps because like people just learn different skill sets and therefore become a better developers at the end of the day.
Yeah, I'm surprised that for some reason I'd imagined that people became more specialized, but I think it's interesting that you promote people being generalists, and I think I understood why, because it makes them more flexible in hopping from one part of the or one area of the project to another, so you're more lean in a sense. One thing you mentioned about games as applications is that they're monolithic. What does that mean?
So that means like they're not very modular, unfortunately, and what you compile at the end is just one big executable. So like there are other architecture like service-oriented architecture, which and microservices, for instance, where you have a lot of smaller applications that they all interact with each other. Whereas with games, that's unfortunately not the case. One of the main reason is the for performance reasons. Just having everything as one binary and executable speed things up significantly. But at the same time, it has its own downsides. One of the bigger downsides is the how long it takes to compile the game and link the game. That's one of the big problems there. It is quite common that it might take sometimes half an hour to an hour to compile the whole game, which is a very long time. So then it impacts the iteration time for developers. Because imagine you make a change and then you would like to view that change and you have to wait for an hour to see, and then you notice there's another problem, so another hour. So you soon realize that you can only do a couple of attempts in a day to test your change, really, which isn't very sustainable. So again, as part of our team, deployment pipeline team, we spend a lot of time trying to optimize the build time so we can compile as quickly as possible. So for us, it takes about 10 minutes, just to give you an example, in comparison to other game titles.
Are there incremental approaches to compiling that you do during development time, or is there reasons that you found that's not a viable approach?
No, definitely. So we did a lot of work to make sure we can reliably build the game incrementally. Um, that's definitely one thing that we did. That had its own challenges because what we do is we have a build farm of about 150 physical build machines, and they all have two CPUs, which is about like with 20 cores, so they are quite powerful PCs. And what we found is the status of these machines between each runs is not very predictable because they might compile the game at a certain change list number at a certain point in time, and then they might not compile anything for a while, and then for a couple of hours, and then they compile, and you see these times are not very consistent depending on when was the last time that the build happened on a PC. So that is one of the challenges to make sure we can keep these times consistent. The other thing we do is we use distributed build systems. So even though these machines have like 40 cores, we still use systems that allows us to use other people's idle cores. So when, let's say, they are not using their PCs, they can contribute to the build farm, and we can use that to compile the code. That's another option. But also having really fast hard disks helps a lot because when you build, you are writing and reading a lot of files to disk. So, like we are using, for instance, NVMe drives on all our build farms and our developers' PC because that significantly improves the time to compile the game. And other things are like looking at the code generally, identifying, for instance, when you find particular file that is slow to compile, we try to simplify that file. For instance, because these are all C++, so they are the C++ code might be including a lot of other header files. So by going through and making sure we are not including everything and or some of the base classes that we don't necessarily need and removing them helps a lot. So these are the challenges there. But I think an area of improvement and potentially, especially with this large scale C++ code, is to use incremental build, but at a distributed level. So let's assume that you are making a change. You're probably touching about maybe less than 5% of the code base. And if you could use the other 95% from other people when they compile the game, then your compile time would reduce significantly. Obviously, we don't have that technology available for us. Like we don't have it. I think there are some tools available in the market that helps, but we haven't tried them. Because if you think about it, like as opposed to everybody has to compile that 95% that they don't change. It's a lot of wasted kind of CPU and power that you can avoid.
It sounds like you were describing that arranging your code in a certain way can actually impact the build time,
That's
but I
correct,
didn't
yes.
understand how. Could you explain that a little bit more?
Sure. So let's say let's talk about the header files. For instance, let's say we are including some header files that we don't need. Because the C++, the way it compiles, it runs a preprocessor that looks at all these header files and try to add them to your basically module when you try to compile them. And the more of those you have, the longer obviously it takes to compile them and process them. So by really removing a lot of these unnecessary header files, it helps a lot. And also, there are techniques in C++ like forward declaring a lot of types. It helps as well because there's a need to include the content of those header files in your compilation module there to compile. That's one of the big things. Also, there are other concepts such as unity builds in C++, which is a technique that's kind of debatable. Sometimes it helps. We don't necessarily use that. That allows basically creating bigger C++ files by including other C++ files inside them. We don't necessarily use that much, but that's another technique to help speed up C++ code. But for us, mainly the things that helps us is removing the code that we don't really need to include, having fast disks and a lot of CPU, and using distributed build systems so we can utilize other people's basically idle cores takes us to a good position.
Okay, maybe we can revisit this in the implementation section. I want
Sure.
to stay high level for a little bit longer and try to understand. Taking Sea of Thieves as an example, what kind of game is it in terms of networking, multiplayer, graphics, or gameplay, or any other aspects of the game you think describe it?
Sure. So Sea of Thieves is a multiplayer cooperative adventure game where there is no predefined story for the game, unlike some other games that have a strong narrative story. The story is emergent based on the interaction of players with each other and their environment. And you have to play this online, so you can't play on your own offline. You have to be online when you play the game. So, and in terms of our kind of architecture, we have a client that people download on their console or on their PC to run. We have a server that multiple clients connect to, and we have a set of services, and those services are not written in C++, they are written in C sharp, and they are using microservices architecture that provide a lot of capability for the game. And that's kind of the structure. And in terms of the graphics, it's very kind of realistic graphics, like the water. If you look at the water, it is very realistic and it's very beautiful at the same time. So there's a lot of effort put in to make the graphic looks great.
Okay. So I understood there's a client, and that's the monolithic application that's written in C++, and it's distributed to the users to their Xbox. Is it also on PC or is it just
That's
Xbox?
correct. Yes. So they can people can play it on PC and Xbox.
Okay.
And server is the same. Server is the same monolithic C++ code.
The server is the same monolithic C++ code that is run on the client.
No, no, no. Server runs in the cloud. Um, so that
Uh,
runs on Azure, and the clients connect to that.
okay, but the server you said is also written in C++, and is there a shared code between the client and the server, or the server is
Yes.
its own?
No, no. So the code there's a proportion of the code that is shared between both client and server because at the end of the day they need to understand how they're communicating with each other. Um, but when we are compiling, we have to compile the client separately to the server because the server, for instance, doesn't have a lot of the code that the client has. And the package for the server that we create, that we upload to the cloud, is significantly smaller than the client because, for instance, the client needs to have or the assets. I mean, what I mentioned was the size of the game can be 50 to 100 gigabyte. And what you find is probably a tiny proportion of that is just executable. The rest of it is just the art and audio assets like the textures, the animation, the sound effects, the visual effects, and all of those constitute most of that data. Whereas a server doesn't need all of those assets because like you're not trying to render anything on the server side. It's mainly there to compute things and be the authority to tell the clients what needs to happen there. So we need to basically make two separate packages, one for the client and one for the server.
Okay, so there is some shared code, but it's compiled separately for client and server because on server you're stripping out or just not including the graphical assets, etc.
That's correct. That is correct. Yes.
And maybe we need to get a little bit into the game design or perhaps the way that the game is structured because it sounds like that there's some shared state or some simulation that's happening that's in common between the client and the server.
Yes.
Not necessarily the part that's rendered, but you said the authoritative state. So what I'm imagining from that is that when I move my character in the game, that the commands that move my character or perhaps the location of my character has to be reflected on the server so that everyone who's participating in the game can get that data, and that because you want things to be consistent, you're doing the same simulation on the client and the server. Is that correct?
Yes. You're absolutely right. Yes. And when I say authoritative, I mean that let's, as you said, like client, let's say calculates its position because like given it's our game, and let's say the game has a ship and the players are on a ship, and the ship is moving based on a certain speed, and so client can calculate where it's heading, the direction and the position in future, and the server does the same thing. And but if the client and server end up disagreeing on where the position should be, the server corrects the client. And that's kind of one of the ways for us to kind of prevent cheating. Because like let's say some people as opposed to trying to, I don't know, let's say they can somehow they could increase the speed that they can sail, that would be corrected back because of the server code there, because that's what it tells the client to do.
That makes sense.
Yes, but as you said, it is running a lot of simulation on the server.
Okay. So far we talked about the monolithic client, the dedicated server, which is in a sense a subset of that client, but we didn't talk about the services, that the part that's written in C sharp. What do those services do?
So services are there to complement the client and server, and they are there to communicate extra information both to server and the client. For example, let's say that your profile information, storing what you like, let's say you are accumulating gold in the game. So that information needs to be stored somewhere and then communicated back. All of that is done through services. Or the other thing we use it is for configuration. So if we want to, let's say, change some configuration of the game, we do that via the services. So then when it's updated, then both the client and server can get that information. Um, Another thing that we use them for is the feature toggles, which is one of the enabler for us to use trunk-based development and manage to stay in the same.
So it sounds like the dedicated server is handling things related to the running state of the game. Like if I'm in the game and I'm playing it, my player's moving around, all the real time stuff, and the services are doing things that maybe don't have that same real time quality. Is that a
Yeah,
rough
yes,
description?
I think that's quite right. Especially like the server doesn't remember any kind of states or anything about the game. So when you start a new server, it starts from fresh. It doesn't remember what you were doing before. Whereas the services are kind of responsible for getting all of that information and pass it to both client and server.
And I suppose that in your talk and in what we've described so far about the continuous delivery related to games, the special part is the client and dedicated server part that's written in C++, because these server services that are deployed on Azure would probably be not too different from ordinary web services that we talk about regularly on this program.
Absolutely, yes, you're absolutely right. That's correct. The main challenge is the client and the server, especially the client side. Because still with the server, as you mentioned, the server is in the cloud, so we can deploy server however many times we want, and that wouldn't have necessarily noticeable impact for players. Whereas the client is the main thing that players are interacting with, and that's the main challenge there. Because every time you update, it would be a friction potentially with players.
Okay. One thing that you mentioned in your talk was that only 5% to 10% of the project consists of code.
Correct. Yes.
What makes up the other 90 to 95%?
We call them assets, which are art and audio assets mainly, and video. So let's say there are like because the game, especially AAA game with a high level of quality, the graphics and the audio, so they need high resolution textures. They need animation models, the whole environment, the whole world, the audio, the sound effects, all of that, and the videos, like the cutscenes that you see in the game, they all consume majority of that 90 to 95%. Like I think our executable for us is probably 150 megabyte, which is not small, but in relatively speaking, when the whole package is like between 30 to 50 gigabyte, 150 meg is very very small percentage of that.
Hmm.
But obviously that's millions lines of code there, so still it's quite big.
Now, when you're creating these builds that take potentially hours to complete, or if you're able to do your job well, get it down to minutes with your parallelized build process, is most of the time in the build going to just the C++ compiler, or is there other processing that's happening on these assets as part of your build pipeline?
It's both. Compiling is a big chunk, but more time is spent on, as you said, processing those assets because they need to be converted to format specifically for a platform that you are releasing on. Let's say our artists working on textures, let's say, they can work in any kind of normal like kind of software, or the models that they develop, let's say they develop it in 3D Studio Max or Maya, but that model we cannot load that direct as it is on Xbox because it's not very efficient. I mean, one of the main reasons is efficiency for us, because what we want to do, we want to load the asset as it is into memory and make sure everything is aligned and is compacted as much as possible, so we don't consume a lot of memory. Because one of the challenges with, especially with AAA games, because of a lot of high resolution assets, is amount of memory that is required to load. So making sure that we kind of strip out any pieces of information that is not relevant for the game, that allows us then to load them better and achieve a better performance, because that means we can get into the game faster because we have managed to load all the required assets faster. So that is quite important, but that part can take a very long time to go through each asset, strip out the unneeded information, and make sure they are compacted and aligned. So therefore, they are loaded faster.
Okay. So at one end of the pipeline, you have the artists that are creating the raw files, or whatever the working format is for those
Correct.
files, and there's a process where they're converted down into the thing that the computer or the Xbox is natively good at rendering.
Exactly. Yes.
And I've heard this part of the process described as a pipeline just on its own, the asset pipeline.
Yes.
So I'm it makes me a little confused because on one hand we're talking about deployment pipeline, then we have the asset pipeline, and it sounds like your team is kind of combining through tools and through processes, combining these into one continuous delivery pipeline. Is that how you think of it, or how do you define and use the word pipeline, or is it context dependent?
No, that's an excellent observation. That's absolutely right. Because you said you could have an asset pipeline. You could also have a code pipeline because like you are compiling the code and generating an output at the end of it. But the deployment pipeline is basically combination of all of these different pipelines that you have. Because at the end of the day, each of these pipelines result in this one package that we create for our players to be able to release to that. And having one kind of looking at all of this as one pipeline and even one team looking after this means that when we are optimizing for the global end-to-end time, because it's not great if we have a super fast, let's say, compile time, but our asset pipeline is very, very slow, because at the end of the day, that's our bottleneck. And if the code is really fast to compile, but then it takes like a day to convert all the assets, we haven't really achieved much, because still the rate that we can release would be by how long it takes for us to convert the assets. So by treating both of them as just one pipeline, because we also have to think about audio assets. Audio assets are very similar to the art asset that we mentioned. They are in the raw format that needs to be converted into the format that can be played on an Xbox. So by treating all of them as kind of one pipeline, looking after them helps massively.
I'm glad that you described it that way because I was planning to ask what is the thing you're trying to optimize.
It's mainly the cycle time, which we call a cycle time, is the time it takes to go through this pipeline, which is basically from the time that somebody has wants to make a change until we can release that change to players. That's kind of the time that we're trying to optimize.
Got it. Okay, I think now's a good time to jump into the implementation. So, how you went from not having a pipeline team to having your team and the continuous delivery pipeline we've been talking about. At the pipeline conference, in your presentation, you described how you implemented continuous delivery for Sea of Thieves, and you said that this was a first for the company. So I'm curious, why hadn't this been done before?
a couple of reasons. I think, especially with I mean, this is a wrong assumption, but a lot of people make, unfortunately, this wrong assumption, and we were making the same wrong assumption, which is because you are releasing once every 3, 4 years, people might assume that there is no value in doing continuous delivery, because they might say that we are working on this code base. It doesn't really matter if it doesn't compile or the game crashes or features are not integrated. They focus on developing these features as quickly as possible and then spend the last part of the project trying to kind of glue all of these things together, make sure the performance is acceptable, make sure the memory is under the budget, the reliability of the game is high so it doesn't crash, it's stable, and bugs are fixed. And they rarely have to maintain that code base after they released. So a lot of practices that we talk about in continuous delivery, like the benefits of maintainability, people don't see that. Even though they're working on the code base for like 3 to 4 years, and they have to deal with maintainability and slowness if you're not really tackling technical debt, they just assume that because at the end of it, the project, they throw away the code and start again, they can afford to do that, which is a completely wrong assumption to make. But the other reason is this is hard. It isn't easy, and like we started this about 4 years ago, and we have made huge progress, but still there are plenty of things that we can improve. So it's not like a simple thing to change, and also requires a lot of cultural change because our developers, for instance, when we started, they were not used to writing tests, and a lot of people still assume that it's not developers' role to write tests, which is not quite right. So having to convince developers that actually they need to write tests and why they need to write tests was quite important, and it could be quite challenging. So I think these are probably the reasons that not like we certainly didn't adopt it in the past, and also not many other companies unfortunately adopt. But as we have seen with the benefits, even though at the moment we are releasing once a week, we can do it more frequent as well if we want to. But I think what we found is releasing once a week is a good rhythm for us. But even if we were releasing once every month, by having these candidates, it just gives us confidence that when we get to that point, we have many candidates potentially that we can choose to release. It's basically looking at the different feature sets in each of these candidates and pick the best one. Whereas in the traditional model, you only have one candidate, and that's the one that you made the day before, which adds a lot to the risk.
I see. So it was hard to implement because you hadn't done it before. It costs a lot in resources. It sounded like you have a team of 10 people or so that are dedicated to this. And on
Yes.
top of this, you had to change the culture, getting developers to be comfortable writing tests, to understand
Yes.
that that's part of their role if they want to create a high quality product.
Absolutely, yes. And also developers like you need a change in mindset for the developers because again traditionally they kind of used to the fact that they go and work on a piece of code on a feature for a week, couple of weeks, and then they check in at the end. So they basically submit this massive change. And again, changing that mindset to say, no, you need to break this down into small increments. That is a skill in itself, regardless of whether you do continuous integration, continuous delivery, or anything. But getting developers to change how they approach solving problems, but not trying to solve the problem at the end, but try to solve it in incremental steps was another big challenge for us.
And how has the team adapted to that?
Quite well. Like I think if we were deciding to go back to the old model, a lot of people would not be happy. I think because once you work this way and you can see that you can make a change, be able to give it to the players within a day or two at most, that's it's very rewarding. Because otherwise, like you're working on a feature and you're probably not going to give it to players for a year, so you're really not going to see the impact of your change. Whereas in this case, you are working and then you are like now and then you give it 2 days later to the players and they can see how they reacted because you can see the community, like if you release a new feature, how they responded, and also that fast feedback that developers get is really really rewarding, I think.
DigitalOcean is the easiest cloud platform to deploy, manage, and scale applications of any size, removing infrastructure friction and providing predictability so developers and their teams can deploy faster and focus on building software that customers love. With thousands of in-depth tutorials and an active community, we provide the support you need. DigitalOcean stands out of the crowd due to its simplicity and high performance with no billing surprises. Try DigitalOcean for free by getting a $100 infrastructure credit at do.co/SERadio.
I see. So you said earlier that it was more sustainable way of working because it's not a continuous crunch.
Absolutely.
And
Yes, that's another important thing because still like some people might crunch, but I think that's the nature of games because like everybody wants people want to produce the best possible version of the thing that they're working on, because it's kind of they're extremely proud of what they are working in. So it's natural that people want to kind of cram as much as possible up to the last minute. But it's certainly like first of all, this is voluntarily, like some people do, and it's not like consistent. Like you might working on one specific feature, you really want to give this out, so you might kind of do a couple of overtimes, but then you go back and you work on your normal.
so in the deployment pipeline, is there a centerpiece of the architecture like something like Jenkins that's your build server that controls everything?
Yeah, we use Team City, but yeah, I got a CI server. Yes.
Okay.
Yeah, we can talk. Yeah, we can talk about those. If you want.
Yeah, let's talk
Sure.
about that a little bit.
Sure.
Like how does it work? You have a bunch of scripts that you configure to run in a certain order, or what does it look like at a practical level?
Yeah. So as I mentioned, we use Team City as our CI server, and for our source control, we are using Perforce, which is a centralized source control system. And we have a bunch of scripts and tools that we've written that we execute on Team City, and they are responsible for compiling the game, converting the assets. We have written a testing framework ourselves, which we run on Team City as well and report the test. But at the same time, we wrote a lot of tools to be able to collect the relevant information when we run tests, to be able to report them to developers. So when a test fails, it's easy for them to identify what caused the failure. And in terms of the size of our infrastructure that we use, we have about 150 physical PCs that we use, and they are quite powerful PCs with two CPUs, with a lot of memory and very fast network and disk and a lot of disk storage. In terms of the amount of data that we generate, I think we generate about 10 terabyte of data every day, so it's quite a lot. And in terms of the number of tests that we have written, we have about 60,000 tests, and I think we run about 4 or 5 million tests per day. And in our tests, about 90% of them are unit tests, and the rest are more tests that focus on larger area of the code, or some integration tests, some performance tests, or some memory tests that we have. Does that answer your question?
Yeah, so Team City is the centerpiece. That's where the control is done of the overall process, it sounds
Yes.
like. Does that also handle orchestration of those 150 machines, or is that a separate piece?
No, that's correct. That it happens through Team City, but given like we have a farm of 150 machines, we also use some monitoring systems to monitor the health of these PCs because at any given time there could be a couple of them that have issues. Either they might run out of disk space, or they might be slow for whatever reason. If they have a hardware fault, they might be offline. So we are using Splunk to monitor the infrastructure as well.
And is the entire infrastructure Windows based?
Yes, it is. Yes, I mean, as you mentioned earlier as well, like we are part of Microsoft. I mean, the main reason that we use Windows is because we are releasing on Windows. But in terms of the tools that we use, we use the tools that make sense. Like for instance, we use Perforce because most of the game companies use have to use centralized source control system. Unfortunately, we can't really use Git first because of the scale, and the other problem is the size of the data and the amount of code that you have to sync and assets. But also with the art assets that we talked about, they are stored mainly as binary format, which means that you can't really merge these files. So it's quite important that when you're editing this, you lock these files so other people would not accidentally change them, because otherwise when you finish, either you have to override their change or you would lose your change instead.
It sounded like if your binary files that come from your art assets get out of sync with the code, that can cause real problems. And that's part of the reason that you were using trunk based development.
Yes, that's quite right. Because some I've heard that some other maybe other games, what they do is they have probably even like a separate even source control system, or even some different branch for the content, like the assets. But as you said, it's a challenge to make sure the game, when the game changes, they can still read those formats and they can go out of sync. And what we found is generally simpler to keep both the content and the code in the same branch. Although I have to say, what we do is the source assets, the raw formats that we talked about, they are not in the same place because like they are quite massive as well, and we don't want everybody to necessarily sync them. So they are kind of separated, but the output of those assets that are converted to the format that can be used in the game are next to the code that we have, which is the game.
It actually reminds me a lot of developing against a large database where your code is heavily dependent on the database schema, and these schema changes always have to go out before your code changes go out. So that's part of the incremental process. First, you change the schema, then you change the code, and there have to be known boundaries for when those changes happen.
Yes, yeah, absolutely. And in the past, like we used versioning as well. So you version your asset. So and then, but you have to make sure you are backward compatible as well. So when you make change, you can still load these different version of assets and update them. But so generally, we found that it's simpler if we keep everything in one branch and don't have and make sure when you sync the head, everything should work as is expected.
Okay. So you call this trunk-based development, and in this case, the trunk must be what you call the main branch in Perforce. In Git, it would be called master, or it might be called trunk in SVN. But you are contrasting this with feature branch-based development. Can you talk a little bit more about that, the differences?
Absolutely, yes. So the main difference is like everybody working the same branch, which is, as you said, main or trunk. Whereas with feature branches, you can have a feature team, they go away, work on a separate branch, and once they finish developing their feature, then they integrate the change back into the main. There were a couple of problems with this approach. One of the first problem is if, let's, as I mentioned, the assets are binary formats. So if you are working on certain assets in your feature branch and somebody happens to make a change to the same assets in the main branch, when you get to integrate your changes back to main, you have to override one or the other, so you might lose that. And what we know is that the longer it takes and the bigger the change is, the more painful it is to merge that back. And this is one of the ideas behind continuous integration. By doing integration back into the main branch frequently, like daily or even more frequently than daily, you are reducing that painful merge conflict to the minimum possible pain. The other problem is when you are working on a separate branch, your feedback loop is extremely long. Because until you merge your change back and integrate your feature into the main game, you're not going to get any feedback about your change. So by working on the same on main trunk, you can check in, and a couple of hours later, you can see that your change how is interacting with everybody else's change. So you get extremely fast feedback compared to the feature branches. And also on top of that, if you have multiple feature branches and you fix the critical issue in, let's say, trunk, then now you have to integrate the same change to multiple branches. And depending on how out of date they are, it could be quite a difficult thing to do. We used to have feature branches, and it wasn't fun at all.
Do any examples come to mind of particularly painful merge experience from a feature branch?
Sure, in one of the games that we worked about like 6 7 years ago, which was a sports game. So we had multiple different sports, and each one was developing their own branches. It kind of made sense at that point in terms of logically, because somebody working on a game of tennis, then they were working on their own branch, and then I don't know, somebody else working on a game of bowling, they work on a different branch. And what we were doing at that point was we were intending to integrate changes back to main at the beginning of the week to make a build so then we can get some feedback. But often what we found was we started this process on Monday and usually took until Wednesday or Thursday until all of these changes were integrated and compiling successfully. So it was very painful and a lot time consuming. And I remember spending a lot of late nights trying to merge these changes back with the help of the developers working on these features. So imagine that you worked on a feature, you don't get any feedback that week. End of the following week is when you get the feedback about your change. So the feedback loop is a lot longer. Whereas right now, as I mentioned, developers work on a feature, they check it in, and potentially we can release that within a day, so they can see the impact of their change.
So it's the difference between an hour and potentially a week.
Possibly, yes. And sometimes it could be even longer depending on how often you choose to integrate. I mean, we were doing it weekly, but it's not uncommon for somebody not to integrate anything and wait until the feature is fully complete. Although it's not really complete because you don't know if it works with the rest of the code base.
Okay. And at the end, if you're using the trunk based development, what you have is something potentially releasable because it has everyone's changes in it.
Absolutely. And one of the important thing is to make sure that trunk remains releasable. So what we do is anytime we are not releasable, let's say the game doesn't compile or some assets are broken, like there's a missing dependency or something like that, that means we can't really release the game. What we do is we stop the line, so to speak, and we lock the depot so nobody can check in any more changes to the trunk. What we do at that point is try to, as quickly as possible, to identify the change that caused this problem. Once we identify that, as opposed to then trying to fix that, because now we are potentially blocking a lot of people trying to commit back to trunk, we identify the change and we back out the change. We basically remove the change from the source control, and the developer responsible can come up with the fix in their own time. We found that it's a lot less stressful because if a developer trying to come up with the fix whilst everybody is blocked, it could be very stressful for developers. So by backing out the change as quickly as possible, we go back to a releasable state and let other people carry on.
Do you have a technique for quickly identifying the offending change?
Well, it's a lot of it is tribal knowledge, but one thing that definitely helps is the fewer changes we have in any given build, the easier it is to identify. When we're looking at, let's say, I don't know, two, three, four changes, it's easier to identify which one contributed to the problem than if you're looking at, I don't know, 50 or 100 or even potentially longer or more changes there. So, by trying to keep the number of changes small, it helps to identifying this. That's the I think I would say is the most important part.
Okay, so it's the number of changes that are batched into a given build.
Exactly. And again, this is a part of continuous integration. They're trying to work in small batches by committing frequently and validating in small batches. It significantly helps because also it reduces the risk because we have found in the past when if there were a lot of changes gone in, each change might work fine individually, but they might interact badly with each other. And you're not going to know that until you are combining this with everything else. So if you are looking at like trying to validate 100 changes together, there's a chance that some of them might just interact badly with each other and you get that kind of failure.
I see.
And another technique that allows us to work to do trunk-based development is using feature toggles. Because one of the challenges is if everybody's working on the same branch and some features are still in progress, which means that we don't necessarily want to release that to players, how to kind of hide these features. Because traditionally, using feature branches is one way of solving this problem because the code is not even on the branch that you are releasing. Whereas what we found is by there are two techniques. One is branch by abstraction. So you could just have, let's say, a different like if else statement. So we if just having different code paths, so we can develop the other code path whilst the other one is being used. That's one way, which is then could be the feature toggles. So by choosing to switch off a certain code path through feature toggles, we prevent players seeing it. And we achieve that in two ways. One is we call it compile time toggle, which at compile time we strip out any code that are behind those features. So we don't actually ship any of that to players. That's one way of doing it, which is good in one way, but at the same time, it's not very flexible. Once it's compiled out, if you need another build with the feature enabled, you have to basically make two builds. Another approach is we use dynamic toggles, and that means the code is not stripped out, still is in the package and in the executable, but we can choose to toggle a feature on or off, ideally even for a different set of players based on certain criteria, and that's where we use our services to help drive that, because we can change the set of toggles, and the services can tell the client to load certain features or not.
Okay, so feature toggles, I understood. I understood that some of them can be static and stripped out by the compiler, whereas others are dynamic and are essentially flags that are evaluated at runtime. But you mentioned a term branch by abstraction, and I didn't quite follow what that was or how that was related.
You kind of have your branches, but like in code. And like as I said, let's say you have an interface and you have implemented that interface in one way, and now you want to come up with a different interface. Let's say you have an algorithm for, I don't know, let's say your path finding. You want to find a path, and it's implemented in a certain way, and you're thinking of coming up with a better way of doing it. And let's say it takes a while for you to kind of write and finish that new algorithm. Again, traditionally, like somebody might just work on the whole algorithm locally on their PC. Once they're happy, they check it in and override the old algorithm. That's one way of doing it, which is not great because you don't get really feedback about your change whilst you are working on this locally. So a better approach is to using if you don't even have an interface, you can create an interface in the first place as a first step and put your implementation as in a class that is implementing that interface. At the same time, you can create another implementation and develop your algorithm in the other class that implements this interface, but nothing is referencing this new interface. So you can easily check in your change and nobody would be using it. You might choose to somehow toggle it on. It could be you could combine it with feature toggles or just locally if you want to change the implementation to use the new algorithm. And once you're happy, you just switch over. And you can leave the old algorithm there in case there's a problem and you want to roll back to the other algorithm. And once you're happy, you can just completely remove the old algorithm and use the new one.
Okay. I think I understand now. So you had some code that instantiates a Pathfinder,
Yes.
and that code's referring to the Pathfinder interface. And maybe the implementation was an A star Pathfinder, and you want to replace it with a something different, like an AI Pathfinder or something.
Yep.
And what you can do is just create a new implementation, and in one branch of code, either perhaps using a feature toggle, you instantiate one or the other.
Exactly. Yes.
Cool. The next thing I wanted to talk about was prototyping. You mentioned some interesting things about prototyping in your talk. One thing you said was that you had a methodology for preventing prototyping code from getting into production. Could you talk about that?
Absolutely, yes. So when we started with this project, because given like we were learning how to work in a different way, we found that it's actually easier if we start with a small core team who understood this concept and like the testing, automated testing, and all the stuff that we talked about here already. So they started and building the foundations for the code base. But at the same time, we wanted to prototype a lot of ideas just to prove them out and make sure we can answer a lot of questions. And we really didn't want to mix these two together. Again, in the past, what we found is that prototype code might end up actually be your production code that nobody really wants, but it's hard for them to go and justify, have to re-implement that again, because somebody might say that, oh, but I have seen this feature now, it looks good. Why don't we just use that? Why do you want to go and rewrite that with a high quality? So what we did was to kind of isolate this core team so they can carry on working on the code base and at the production quality, while at the same time allows us to answer those questions. We formed a different team, which was the prototype team, and they even use a different engine. For prototyping, we use Unity engine, and for the main game, we are using Unreal for the people who are interested. And by actually separating them, there was no way for us to actually bring the code back from prototype into production. So we could be almost like fast and loose on prototype code base. Obviously, there was no need to write a lot of tests. You just had to have some small number of tests to make sure, like, for instance, the game doesn't crash. And they could go really fast, kind of answer a lot of questions and even delete the code, rewrite it again, however many times they needed. And once we answered those questions, we went back to Unreal and started implementing it from scratch.
Okay. Was what you were trying to prove in the prototyping phase the viability of the game, or was it the continuous delivery process?
No, it was mainly the game itself, not the process. Sometimes, if mainly we use the prototyping to answer questions about the game itself, but sometimes if we were going to evaluate, I don't know, a different technology or a different tool to use, we would use that. We would prototype that as well, but that would be a separate branch completely. Again, it's a branch that we create to answer this question and throw it away. It was never intended that we work on a separate branch and then bring that into our main. That was there mainly to basically experiment, because what we what we don't want to happen is you spend a lot of time trying to improve the quality of something that you're not sure you're going to need. Because if it turns out that feature that you're working on is no use, there's no point in, let's say, adding any tests for that, because you're going to throw that away at the end of your experiment. So it helps a lot with experimentation. But that was kind of how we started at the beginning. But now we are prototyping more and more in Unreal itself. But again, I think because now we feel like we reach a certain maturity level that our developers understand the difference between the prototype code, the production code, and the dangers in trying to kind of write prototype code when you give that to and potentially release that to, I don't know, 4 or 5 million players there and causing incidents and crashes in the game, which nobody wants to do. So now that kind of we are kind of more mature and understand this better, we are using prototyping using Unreal, but again on a different branch. And the purpose is again to just answer some questions, and then go back to the main branch and implement that feature from scratch.
That was actually packed with a lot of information, that response, because many of our listeners may not know about game engines, and maybe we could say something about what a game engine is for and how Unity and Unreal are different.
Sure, yes. So game engines are, in a way, like engine of the game, and a lot of kind of they provide a lot of libraries and functionality similar to frameworks. If you think about it, um, that like let's say there is a networking library, there's a physics library, there's a rendering library. So you could use those to develop your game as opposed to have to go and implement almost low level functionalities from scratch. And the idea is that those are reusable part of the game code that potentially other games could use. That's why people try to combine them all together and release them as an engine. I think, as I said, probably the closest thing is like frameworks that other people develop. Let's say .NET framework is another example that you can write .NET code that uses the framework itself to achieve your desired outcome. And we have, like as I said, we use Unreal and Unity. Those are the two engines that we use. And at the time, we found that Unreal suited our needs better compared to Unity for what we were trying to achieve.
My impression of Unreal was that it, for C++ projects, a lot of companies or teams will choose Unreal, and Unity had some different options in terms of programming languages. You could use C sharp, you could use like a JavaScript like scripting language, and it wasn't necessarily as geared towards squeezing the last bits of performance out, but was really good for prototyping.
Yeah, no, absolutely, that's correct. That's exactly right. Although Unreal has a concept of blueprint, which is kind of like scripting, but it's visual scripting, which you can kind of have nodes and then lines that basically each node achieves something, and then you connect them so you can kind of create a flow of actions happening. And the idea that they have is by using this, then you can in theory prototype in Unreal as well, which is what we use for prototyping. But that's you're quite right in terms of the difference between the two. A lot of AAA games still prefer Unreal, but I'm sure Unity is catching up and improving a lot.
But it does seem to provide a hard barrier where some code written in Unity is not really compatible with Unreal, and that's how you're able to achieve that clean separation.
Correct. Yes, absolutely. Yes. Yeah.
Great. Well, I think we covered most of what I wanted to talk about in the implementation part, and I wanted to talk more about quality and testing.
Absolutely. Yes.
The next thing I wanted to talk about is quality and testing.
Sure.
First, how do you judge the quality of a game?
That is it's an interesting topic for us as well, because I have to mention before we actually released the game in March, for about a year and a half, we were releasing the game to small number of players, which we had a program called Technical Alpha. So a lot of people could get the game and play the game, and that was one of a hot topic for us to discuss because we were saying what is the accepted level of quality, especially like for instance, do we expect the same level of quality when we are releasing the game to I don't know, let's say 10,000 players versus when we release to 5 million players? Should they have the same quality? Should we not have the same level of quality, but at the same time we want something that when we release it still visually looks good. So there was a lot of discussion happened, but still, and like is a topic that we discuss, especially given we are, as I mentioned, we are trying to make sure we have a daily release candidate. So this topic keeps coming up and say this bug that we have, is this really prevent us from shipping the game, or is this actually okay? We our players would accept that. And I think a lot of it is also related to the expectation that players have from your title and your game. But what we generally say is if something blocks people from progressing in the game, that is usually a blocker and is not accepted. Because we don't want it to be the case. We want people to still be able to play the game. maybe there is a workaround, maybe there's a bug, and there's a workaround that we can communicate. If we do that, then we can say, actually, we just communicate this and then we fix it. Especially given we are releasing weekly, we can release it in the next release. But if you find that something like, I don't know, you trying to sell an item in the game, let's say, and it crashes, and means that then players cannot play the game anymore, that is a blocker and we don't release. Yeah, visually, again, it depends on who you ask. I think, like, for instance, artists probably, obviously, they would like the quality to be amazing, but sometimes we can afford to not hold back a release to fix some visual glitches. But again, it completely depends. It is, I think, quite subjective.
Okay. So we talked about manual testing and the army of testers that you have, and how you're trying to reduce your reliance on manual testing and focus more on automated tests. And you said that I think 80 to 90% of the tests were unit tests. So let's talk a little bit about the details of the implementation. What are these tests like? How are they written and how are they run?
Sure. So in Unreal, we could write two types of tests. We can write them in Blueprint, as I mentioned, with that kind of visual diagram to say, like, you are launching a client, then you expect this thing to happen, and this is you're certain that certain thing happened. And you can easily do that in Blueprint visually. And that's how we started. The benefit of that is it's a lot easier to then write tests. But what we found is these tests take a lot of time, a long time to actually run. And they're very complicated. And you can easily create these complicated blueprints that nobody really understands how they work. And you can't really enforce any styling or anything on them. So we tend to move away from that now, and we try to write our tests in C++ code in the engine itself, because Unreal comes with an automation framework itself. But when we started, it was lacking some of the functionalities that we needed at the time. So we ended up expanding that and give more functionalities to that. So we are directly writing our test in the game engine.
Yeah, so the blueprint is in some sense easier to write, but it can be hard to understand. It's hard to maintain because you can't necessarily look at it and even understand what it's trying to test.
Yeah, that could be the case. Yes. Yeah.
And on top of that, it takes a long time to run.
Yes.
So now you're moving towards writing more tests in C++
Correct.
in the engine itself.
Yes.
And you mentioned that Unreal has its own automated testing framework, but that didn't quite meet your
Yeah.
needs.
So we kind of had to expand that. Yes, we had to switch to write most of our tests in C++. Uh, they were easier to maintain and they were significantly faster to run. Obviously, the downside was it needed some basic training in order to be able to write these new tests, but they were more reliable tests at the same time. One of the challenges we have, as I mentioned, we have about 60,000 tests, and we get some flaky tests. And these are the tests that are non-deterministics. So, which means that you might run them once and they might fail, and with the same code, you run it again and they might pass the second time. So, you're not really sure if the problem is with the code or with the test itself. And what we found is actually a lot of our tests that were written in Blueprint were these flaky tests there. So that was again another reason to uh, not write any new tests in Blueprint and instead try to write them in C++. The main problem with flaky tests is that developers then lose confidence because they just run it again and it works. So even if it fails on the next time, they might just even ignore it. They say, "Oh, I'm probably not related to what I've changed. Is the test that is not deterministic." So the number one problem is that people lose confidence in the pipeline and our automation system, but also running the test again takes time. So you're adding time to your end-to-end time there. So by tackling this flaky test, you not only you improve the confidence, but also reduce the time it takes to run these tests. And what we found is actually having fewer tests that are deterministic is much better than having loads and loads of tests that are non-deterministic and you can't really rely on them. So what we do is when we find a flaky test, we try to quarantine them, and either a developer tries to fix the test, and in this case, if it's a blueprint, ideally they even try to rewrite it in C++ code. But if it turns out that the test isn't really providing value or is not really fit for purpose, we go and just delete that test because we rather not to have that test as opposed to having this test that gives us a lot of noise. But it is really important to stay on top of these flaky tests.
Okay, so it sounds like a test that is flaky, which means basically it's non-deterministic. Sometimes when you run it, it passes, and sometimes it fails. You consider that to be just as good as having no test at all.
Pretty much so, yes. Yes. I
Okay.
mean, which is a bit controversial, and not some people might disagree. But at the same time, if they fail and then kind of people lose trust, and even when they fail, people stop looking at them.
Okay. So it might actually even have be worse than having no test.
Yes. Yeah. Because what we do is when, as I said, when we remove a test because we think this test isn't valuable, and if it turns out that we were wrong and or there was a bug that we missed, we can go at that point. We definitely know that there's a value in this test, so we can go and write the test properly this time.
Okay. Do you have an example of one of these flaky tests to illustrate the point?
Yeah, absolutely. So let's say tests that kind of we had tests that were failing or they might pass depending on the order that they got executed, but those were because they were not really isolated. So it could be a test that ran beforehand that changed the state of the game or something, and then that this other test relied on because it was not setting it at the beginning correctly, you're just relying on a state to be set to a certain value, then it might just fail or pass depending on which other test ran beforehand. So that was one cause for us. The other one was sometimes, especially given like our game is client and server, so we had a test that kind of launches the client, then waits and launches the server, and then waits, and then they should connect with each other. And how we started again, because given like we were learning how to write tests, we were kind of putting some random waits to say, I don't know, let's say I launch the client and launch the server and wait for 10 seconds. I would expect them to connect. And that might work fine to begin with. But as we add more content to the game, and it might take longer to load. So you gradually takes longer to load, and then that 10 seconds might not be enough. So when you get to about 9 seconds, if you happen to run on an agent that is slightly slower, that might be just 11 seconds, which means that your assert would fail because it takes longer than 10 seconds. And you might run another agent that's slightly faster, and it might work. Also, relying on external dependencies like a remote service. If that service is down, your test might fail and then it might come back online and your test passes. So these are some examples I can think of.
Okay, so the first example was some relying on some precondition that you hadn't set during the test. So I don't know, maybe some particular object being in some particular place or
Exactly. Yes.
something like that.
Yes.
The second one was something timing dependent
Yes.
that had to do with loading assets or something of that nature. So relying on some precondition that was timing dependent. And the third was a external service, which may or may not be available.
Yeah.
So how did you solve those problems?
So, the first one is obvious. So when you find that this test wasn't setting the state correctly, is to make sure like you fix that. I mean, obviously it's hard to find because it's completely order dependent. The other one is like we almost don't write any tests anymore that wait for certain seconds. We always try to change how we test this so we don't have to do that. And ideally, even we try to have as few tests as possible that have to rely on a client being launched and a server being launched and like all of these things because that shows that that's not really a unit test. That's like kind of more like an integration test. So it's questionable whether like how many of those you should have in the first place. I mean, you need to have some that kind of want to make sure that your client and server connects. But we tried again not to rely on timeouts because, as I said, like as the game size increases, those timeouts would eventually fail. And the other one about external dependencies and services is either trying to mock them so we don't have to really make those calls if we can, or alternatively trying to run those services locally on the same box that we're running our client or server, so they don't have to do any external communication. Let's say if the connection to internet drops for a few seconds, you don't want your test to fail. So by running everything on the same machine, then you eliminate some of that as well.
One thing we didn't talk about yet was the actual deployment process, how the bits get onto the client's Xbox or PC. Could you talk about that?
Absolutely. So the releasing a game for any platforms, it requires a certification process by the platform holder, like Microsoft, Sony, Nintendo, and even releasing a mobile application to iOS is fairly similar in the sense that you have to go a certification process, and the main purpose of that is to ensure that the quality of that platform meets the expectation that the platform holder has and the promise it gives to the consumers of that platform. So that's why they are there. So they are there for valid reasons, but at the same time, it could add significant amount of time to the end-to-end time. Uh, but for us, what we do is we when we make our packages for clients for both Xbox and PC, we then have to upload that to this portal for the certification team to verify the game is working as expected. And then once they approve, then we can release that to our players. But given we are releasing so frequently, I think we have done about 180, 190 releases so far. Obviously requires significant amount of resource from Xbox certification team to verify. So what they had to do was they kind of through a lot of kind of great conversation and collaboration with them, we came up with a different model that helped out quite a lot. We got to the point where after the couple of certification passes, they kind of trusted us to make sure the quality meets their expectation. So we could release a lot faster. We still submit through the certification process, but we are kind of in a almost like a bypass mode where they let us go through the certification process. But what they do instead is they're using telemetry in production to monitor the game. So, for instance, the crash rate, they are monitoring our crash rate. And as long as it remains under a certain level that we agreed, then everything is great. We can still release as fast and as regularly as we are doing now. But if for some reason we're not careful and we make mistakes and the quality drops, then they can step in and try to put more pressure on us and put more checks to make sure the title that we are releasing meets their expectation.
Are there libraries or other code that you have to bake into the binary so that you get that telemetry data, or is it somehow automatically provided by the platform?
Yes, they are provided by the platform, and they are quite useful for us as well because we can monitor now that the game is released for 5 6 months roughly. It really helps us as well because we can see that when basically the quality and stability of our title using the same set of telemetry and information there. Obviously, we do a lot of work, and probably this is a topic on itself. We do a lot of work on telemetry to post telemetry about the game, about how people play the game. Because what one thing again, continuous delivery allows us to do is experimentation. So, and even do hypothesis-driven development. So, if somebody thinks that we need to improve a metric, we can work on a feature, release that, and get some telemetry to prove that was a good idea or not, and respond accordingly. So we do a lot of post a lot of telemetry ourselves, but we at the same time we use a lot from the platform itself.
Does that go back to what you were talking about with the feature flags, or I think you called them feature toggles, so that you can sort of start ratcheting up some of those toggles to give to a subset of user? Or is there another mechanism for how you test?
That is the intention. That's definitely the intention that we use the feature toggles to release them to a subset of players. At the moment, when we just release to everybody, but we are working on improving that. But we are using other mechanism to get some feedback and release the game. Again, platform provides like these capabilities for us, having a different set of players in it's called a flighting program, where you register your users in different kind of these different programs, and then when you release, it only goes to this number of players. So we are using that as well. But that means, again, is you basically need to submit 2 packages to go to these different audiences. What we like to do ideally is to still use the one package and release it once, but then different set of players receive different set of features. But that's for future work.
Okay, that's for future work. Perhaps we can have a follow-up.
Absolutely.
Well, I think we're up against time, Jafar. So before I wrap things up, is there anything else that we haven't covered that you'd like to talk about?
No, I think we covered quite a lot. Again, like the one thing that changed for us since we launched is now that we have to operate the game, it comes with its own challenges. But again, that's probably a topic on its own. But other than that, I think we covered quite a lot.
Great. I mentioned the talk that you gave at the Pipeline conference, and you told me offline that there was also a version of that talk that you gave at GDC. So I'll include both of those in the show notes.
That would be great. Yes, thank you.
Okay. Well, Jafar Soltani, it was great having you on Software Engineering Radio. For our listeners, thanks for listening, and we'll talk to you next time.
Thank you. It was a pleasure being on your podcast. Thank you.
Great. For Software Engineering Radio, this has been Nate Black. Thanks for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.